You ever find yourself stuck on a big decision, feeling like you've got limited info, trying to hit a moving target maybe?
Oh, definitely. Like, when's the right time to hire someone or sell an asset?
Exactly. Or even something really critical like uh, deciding when to stop a clinical trial if things look a bit iffy. You never quite feel like you have all the information you need, right?
Yeah. It's always that feeling of uncertainty.
Well, today on the deep dive, we're really going to get into this fascinating area called optimal stopping.
Right. And to really, get a good grip on it, we've pulled together insights from a few different places. We're looking at some cutting edge machine learning research,
Okay.
some foundational stuff from MIT lecture notes on dynamic programming, a paper on how it's used in medical statistics for clinical trials, and we'll even dig into the classic secretary problem.
Nice. So our goal today is really to unpack this whole optimal stopping idea from these different angles and hopefully see how these concepts can actually help you make smarter choices.
Yeah, whether that's at work or in your personal life, or maybe you're just curious about how these strategies get figured out.
We're aiming for those moments where it just clicks,
Yeah.
those aha moments. So hopefully you'll start seeing these kinds of sequential decisions, the ones with uncertain futures, in a new light.
Exactly. We'll try not to drown you in super technical jargon, but
Right.
we want to pull out the really key ideas and maybe some surprising bits from all these sources, just to give you a clearer and hopefully useful picture of optimal stopping.
Okay, sounds good. Let's dive in. So we're starting with the machine learning angle, right? This research on deep optimal stopping.
Yeah, this is about using neural networks, AI, to figure out the absolute best time to pull the trigger on something when you're facing a sequence of choices over time.
And what's really cool here, it sounds like, is that it's not just about automating it. These networks can handle way more complexity than the old math methods could.
Precisely. They can tackle problems that were just, well, too messy before. And that means they might find patterns or optimal timings in really complex situations that we wouldn't have spotted otherwise. High stakes decisions, things like that.
The paper mentions things like affine functions and real U activation functions. Okay, that sounds technical.
It does, but think of them like the tools the network uses. They're like building blocks that let the network learn really flexible rules or boundaries for when to stop versus when to keep going.
Ah, okay, so it's drawing the line, essentially.
Kind of. And often the network doesn't just spit out a stop or go, it might give you a stopping probability. Like, there's an 80% chance that stopping right now is your best move.
That makes sense, dealing with uncertainty.
Exactly. It's more nuanced, which is often more realistic.
And the research suggests that if these networks are complex enough, they get really close to making the actual optimal decision.
Yeah, almost optimal is the term they use. With enough layers, enough complexity, they can get remarkably good.
But one of the big challenges is figuring out the continuation value, right? What's that exactly?
Right, the continuation value. Think of it as the expected payoff if you don't stop now. What's the potential value of waiting for the next opportunity or the one after that?
Versus what you get if you stop now.
Exactly. Estimating that future potential accurately is, well, it's often the hardest part. The researchers use techniques like Monte Carlo simulations, basically running thousands of possible future scenarios, and they also make some smart assumptions to simplify things.
Okay. And they're not just giving one answer, they give a range, using point estimates and confidence intervals.
Yeah, that's important. They acknowledge the uncertainty. They use stats like the central limit theorem to basically say, here's our best guess for the optimal value, and here's a range where we're pretty confident the true optimal value lies.
Right.
It's about being realistic about the fuzziness.
So what kind of problems did they test this on?
They picked three really different examples to show the breadth. First was pricing Bermudan max call options. These are financial things.
Right, options.
Yeah, where you can exercise the option on specific dates before it expires, and the payoff depends on the maximum price of several underlying assets. The trick is deciding when to exercise it.
Okay, complex finance stuff.
Then they looked at callable multi-barrier reverse convertibles, another mouthful.
Ah, yeah.
Also finance, again, lots of complex rules about when it might pay out early. You can see in the paper, like in Table 3, it takes serious computing power to train these models. It shows you the scale of complexity.
Wow. And the third one?
The third one I thought was really interesting. Optimally stopping a fractional Brownian motion.
Sure, what's that?
It's a mathematical process, kind of abstract, but it's used to model things that have memory, where the past influences the future more than just like random chance, think stock market trends maybe, or river flows.
Uh,
And table 4 in the paper shows the results. They calculate the optimal stopping value for different levels of this memory, measured by something called the Hurst exponent, h. So if h is high, it means trends tend to persist. What goes up keeps going up. If h is low, it tends to reverse. If h is 0.5, it's basically random. And what they found is that the optimal time to stop, say to take profit, changes dramatically depending on this h value.
so the nature of the randomness or the trendiness really affects the best strategy.
Exactly. When h was near zero point 0.5, the optimal value was near 0, but it went up significantly as h increased, suggesting you should let profits run longer if there's strong positive persistence. It really shows the power of the method to adapt the stopping rule to the underlying characteristics of the process.
Fascinating. So that's the AI approach.
Yeah.
But you said optimal stopping has deeper roots. Let's talk about dynamic programming from those MIT notes.
Right, dynamic programming is sort of the classic fundamental way to think about these sequential decision problems. The core idea is breaking a big problem down into smaller, overlapping steps.
How does that work for stopping problems?
You usually work backward from the end. You start by figuring out the value or cost at the very final stage. They call this the terminal reward or cost to go function.
Okay, the end result.
Yeah. And then you use that to figure out the optimal decision and the resulting value at the second to last step, and then the third to last, and so on, all the way back to the present.
Working backwards in time.
Exactly. And the notes mention that certain properties of these value functions, like convexity or monotonicity, can make things much simpler.
What do those mean in simple terms?
Well, convexity might mean there's a kind of optimal middle ground, and going too far either way is bad. Monotonicity could mean that as something increases, the value consistently goes up or down. If the problem has these nice structures, finding the best policy is often easier.
So the algorithm figures out the value at each step based on the value of the next step.
Pretty much. It's like planning that road trip backwards, like you said. Knowing the final destination helps you figure out the best place to stop the night before, and knowing that helps you figure out the stop before that.
Got it. The notes use an asset selling example.
Yeah, asset selling with irrevocable decisions. It's a great illustration. You have something to sell, like a house or a stock, by a deadline.
Okay.
Each day, maybe, you get an offer. The offers are random, but from some known range or distribution. You have to decide right then, accept the offer and you're done, or reject it and wait for tomorrow's offer. But if you reject, that offer's gone forever.
The irrevocable part.
Right. And the goal is to maximize your expected final selling price.
So what's the optimal strategy?
Dynamic programming shows it's a threshold policy. For each day left before the deadline, there's a specific threshold value. If the offer you get is above that day's threshold, you accept. If it's below, you reject and wait.
And the threshold changes.
Yes, that's the key.
Yeah.
As the deadline gets closer, the threshold generally goes down. You become less picky because you have fewer chances left to get a better offer.
Makes sense. You get more desperate.
Kind of. Now, contrast that with asset selling with offers retained. Here, if you reject an offer, you can still accept it later. You can always choose the best offer you've seen so far.
Okay, so you have a safety net.
Exactly. And that changes the strategy. Now, the optimal policy is often stationary. There's just one threshold, and it doesn't change over time. You just compare the current offer to the best you've seen before and this fixed threshold.
Why is the threshold higher in this case?
Intuitively, because you have more flexibility, since you can always fall back on a previously rejected offer, you can afford to hold out for a really good one. Your benchmark is higher.
Okay. And these thresholds define the optimal stopping set.
Yeah, basically the conditions or values where stopping is the best move.
The notes also mention LQR, linear quadratic control.
Briefly, yeah. It's another area where dynamic programming gives really neat analytical solutions. It applies to systems, like maybe controlling that helicopter they mentioned, where the system's behavior is linear and the costs you want to minimize are quadratic.
So minimizing fuel use and deviation from a path, maybe?
Something like that, yeah. LQR finds the optimal control inputs. They also mention LQG, which adds randomness or noise to the system, and this interesting idea of certainty equivalence, where often the best strategy is to act as if the random noise was just its average value. It's another example of DP yielding powerful structured solutions.
All right, so we've got the theory, the AI. Let's get really practical.
Yeah.
Clinical trials and futility stopping. This seems super important.
Absolutely critical. Clinical trials cost a fortune and take ages. Futility stopping is about asking, partway through, is there any realistic chance this treatment is actually going to prove effective if we continue?
To avoid wasting resources.
Resources, yes, but more importantly, to avoid keeping patients on a treatment that isn't working or maybe even causing harm when it's become clear it's unlikely to succeed.
So how do they decide when it's futile?
There are different rules. Some use conditional power. That's like saying, given the data we have now, what's the probability we'll get a statistically significant result if we run the trial to the end? If that probability drops below a certain level, say 10% or 20%, maybe you stop.
Okay, based on projecting forward.
Right. Other rules look directly at the results so far. Are the interim results looking really poor? Is the treatment group doing no better or even worse than the placebo group? That could also trigger a stop. The paper mentions specific rules like rules 1, 2, and 3 that formalize these different approaches.
And there's a distinction between stopping based on whether the treatment works at all versus whether it meets a specific target.
Exactly. Some rules focus on the null hypothesis, no effect. Others on the alternative hypothesis, a meaningful effect. It's a subtle but important difference in what triggers the stop.
Does stopping early mess up the statistics?
It can, yeah. If you have rules for stopping early, especially for futility, it can affect the overall power of the study, its ability to detect a real effect, and the chance of a false positive, the type I error. So you usually have to account for this in the design, maybe by planning for a slightly larger sample size initially.
The article talks about optimal two-stage designs. What's that?
That's a design with one planned interim look at the data where you might start for futility. The optimal part is about figuring out the best time to take that look and the best rule to use for stopping, often to minimize the average number of patients you expect to enroll.
Minimize cost and patient exposure.
Exactly. Table 2 in the paper shows some examples like maybe the optimal time for the interim look is when you have half the data, an information fraction of 0.5, and it gives the probabilities of stopping then if the drug doesn't work versus if it does work. These optimal values depend on your desired overall error rates and power.
And three-stage designs are even more complex.
Naturally. 2 interim looks means optimizing 2 time points, T1, T2, and 2 stopping rules. Table 3 gives some examples for those, showing it gets complicated quickly.
There's a simulation study, too, comparing Rule 2 and Rule 3.
Yes, Table 4. This is really insightful.
Okay.
It shows what happens if your initial assumption about how much the results will vary is wrong. Rule 2 stops based on testing the no effect idea, while Rule 3 stops based on testing the meaningful effect idea. And the simulation shows that the probability of stopping early can be quite different between the rules, especially if that variability assumption is off. It really highlights that choosing the rule isn't just math. It's about what question you're trying to answer. Is it unlikely will prove any effect? Versus, is it unlikely will prove the specific effect size we hoped for?
Huge practical difference for researchers.
Absolutely. It links the stats back to the real-world goals of the trial.
Okay, wow. From clinical trials now to something, maybe a bit more fun, the secretary problem.
Ah, yes, the classic. Also called the marriage problem, Sultan's dowry. Lots of colorful names.
Huh. So what's the setup?
It's a beautifully simple model of that explore-exploit trade-off. Imagine you need to hire the best secretary out of, say, N applicants. You interview them one by one in random order.
Okay.
After each interview, you have to decide immediately, hire this person or reject them and see the next one. The catch is the decision is final. You can't go back. And your only goal is to maximize the chance you pick the single best applicant overall.
But you don't know who's coming next.
Exactly. You can rank the current applicant against those you've already seen, but you have no idea if the best one is still out there or if you just rejected them.
So hire too soon, you might miss the star. Wait too long, the star might have already passed you by, and you end up with someone mediocre.
That's the dilemma. Exploration versus exploitation. How long do you keep looking, exploring, before you commit to the best you've found so far, exploiting?
And there's his famous answer.
There is the 1N law. It's surprisingly simple. The optimal strategy is reject the first N applicants outright.
Okay, is that number? About 2.718. So reject roughly the first 37%.
Exactly. That's your baseline setting phase, your exploration. You just observe them to get a feel for the quality range. Then, after that initial group, you hire the very first applicant who is better than everyone you saw in that first rejected group.
The first one to beat the benchmark.
Right. If you get to the end and no one beat the benchmark, you have to hire the last applicant.
And the amazing part,
The amazing part is that using this strategy, your probability of picking the absolute best applicant is about 1M, or roughly 37%.
Regardless of how many applicants there are, 10 or a million.
Pretty much. As n gets large, the probability converges to 1M. It's often called the 37% rule. You can find graphs showing this convergence. It's quite striking.
Wow, that's really counterintuitive.
It is. The math behind it involves figuring out the probability of success, PR, if you reject the first R applicants, and then finding the value of R that maximizes that probability. The formula involves a summation, but it leads to that near result.
So the key is defining a candidate as someone better than all previous ones.
Within the strategy, yes. After the rejection phase, you're looking for the first candidate, in that sense, someone who surpasses the maximum quality seen during the rejection phase.
Now, this assumes a few things, right? Like the applicants don't know the strategy, and you know it knew beforehand.
Correct. Those are key assumptions of the basic model. Real life is often messier.
Are there variations?
Oh yeah, lots. What if you want to pick one of the top candidates? What if you get multiple chances to hire? What if your goal isn't just the best, but maximizing the expected rank, like getting someone in the top 10%? These all change the optimal strategy and the success probability. It's a really rich problem.
Okay, so we've covered a lot of ground here, from AI to theory to trials to secretaries. As we wrap up, what are the big takeaways for you, the listener?
I think the core idea is this. Optimal stopping is about navigating sequences of choices under uncertainty. It always involves this fundamental tension between gathering more information, exploring, and committing to the best option found so far exploiting.
And thresholds are key.
Thresholds are absolutely key. Whether it's an offer price, a statistical measure, or just a number of people to observe first, these thresholds define the boundary between continuing and stopping. And it's always about weighing the current reward against the expected value of continuing.
What was the most surprising thing for you in all this?
You know, that 1M rule in the secretary problem still gets me. It's just so elegant and unexpected that such a simple rule gives you a constant 37% chance no matter the scale. That, or maybe just the sheer computational muscle being thrown at these problems now with machine learning and finance, it's pretty wild.
So for you listening, think about where this applies in your life. Have you faced these kinds of when to stop looking dilemmas?
Yeah, searching for a job, a house, maybe even deciding when you've done enough research on something and just need to make the call.
How do you implicitly weigh exploring more options versus grabbing what seems good now? It's something we do all the time, maybe without realizing the underlying math.
Which leads to a final thought to chew on. In today's world, we're often flooded with information and choices. How can we use these optimal stopping ideas consciously to avoid getting stuck in analysis paralysis and actually make decisions with confidence?
Or maybe, when is it okay, or even better, to ignore the mathematically optimal rule? Are there times when gut feeling or ethics or just plain practicality should override the calculated best time to stop? Something to think about.